From what we've seen so far, we know there are a lot of similarities between electrostatics and gravitation. We can find the force between two charges using Coulomb's law, and it looks a lot like the force between two masses from Newton's law of gravity. We use little g to represent the force of Earth's gravity on a given mass, and we can define E to be the electrostatic force on a given charge, which would be newtons per coulomb instead of newtons per kilogram for little g. We could do what we need with this and Newton's second law, but it turns out that it's more convenient to use energy for some problems. So when we started Physics 1, we had the simple form for gravitational potential energy, which was just mgh. And then when we went from F equals mg to the full Newtonian law of gravity, we had to define a new potential energy. If you check your notes from the previous course, the new potential energy was written U equals negative gm1 m2 over r. And again, the big deal here is the r on the bottom is not squared, because that would take us back to gravitational force. The other thing is the energy is negative. The negative value of energy means you have to put energy into it to separate these two masses. The electrostatic version looks very simple. It's U equals K Q1 Q2 over R. You notice we don't have the negative here, and the reason is if the two charges have the same sign, our total energy will be positive, which means they'll move away on their own, and we could actually get energy out of them separating. If one's negative and one's positive, then we're back to having to invest energy to separate them. Just like with a collection of masses, we can find the potential energy of a collection of charges by adding up all possible combinations of that KQQ over R formula. This is one way you commonly see it written, where we have U is 1/2 the sum where I and j go from 1 to n of k, qi, qj over r. We have the restriction that I can't be equal to j, because then r would be 0. We get a mess. That would be the self-energy, which is certainly not something we're considering here. The factor of 1/2 is because if you do this, for example, you'll have the energy between Q2 and Q3, and then later you'll have the energy between Q3 and Q2, so you'll count everything twice. Just as we consider the field to be the force per charge or per mass, we can define a potential energy per charge or per mass. We call this gravitational potential in the first semester and electrostatic potential now. This is not the best name for it because it's easy to confuse potential with potential energy, but they're completely different. Now, you probably didn't actually look at gravitational potential in Physics 1. It's pretty common not to. If we were using mgh as our potential energy, gravitational potential would just be gh. It's the potential energy divided by the mass. If we use the same approximation that gave us g in the first place, and that is g is constant, we could get rid of the g and we could say that height is essentially the same thing as gravitational potential. Now, where would we ever use this? Let's say you have a hill near your driveway and you want to dig it out level with the driveway and build a garage. It's not easy to see how much dirt you need to remove to make things level, but you can do this with what's essentially a simple hose. You have a particular height here, over here where it's flat, and you climb the hill, and at a lower height, the water here will be at the same absolute level as the water here. You might have heard the phrase, water seeks its own level, and this is what that means. You can also see this from first semester physics when you were looking at the height of fluids in differently shaped containers. They're all connected at the bottom, so even though they have all these weird shapes and diameters, they all have a common level here because that fluid is coming to a common gravitational potential. That means the surface of the fluid is an equipotential. All parts of it have the same gravitational potential, so all parts of this and this and this and this. Since g is pretty much constant over distances like this, what it also means is all the top surfaces have the same height. This is about the only use I know of for gravitational potential, but the other one is really neat. The rate of flow of time in a gravitational field depends on the gravitational potential, not the force, not the potential energy. And at the end of the course, we'll look very briefly at general relativity, and we'll see that. It's really kind of cool. Common symbol for potential is the Greek phi. Notice this is the lowercase phi, not the uppercase that we used for flux. Now, electrostatic potential is something we use a lot more often. Let's arrange everything that we've discussed in a way that shows their relationship. So here's our Coulomb's law, the starting point, the force between two charges. If we say what is the force per charge and divide one of them out, we get the field, which is kq over r squared. If we integrate the field per distance, we get the potential. If we take the potential and multiply it by the charge again, now we're back to potential energy. We could go from potential energy to force by differentiating. So we can go from one of these to the other, and we have this nice sort of table that puts them all together. This is really kind of a big deal. We had the same thing in Physics 1. We might not have talked about gravitational potential, but we had these same relationships between these things on the top, the force and the energy, and then the force per mass and energy per mass here on the bottom. So the field we can think of as telling us the force that a mass or charge would feel if it were present. The potential energy tells us about the potential energy that mass or charge would have if it were present. The electrostatic potential comes up much more often than the gravitational potential, and the name we usually use for it instead is voltage. So if you ever get confused, you can think of voltage being very much like height. First of all, it only makes sense to talk about the voltage between 2 points, just as it only makes sense to talk about the height, which is the distance between 2 points. If one point seems obvious, like the floor, if we're talking about someone's height or we're talking about hanging a picture at a certain height, a lot of times we'll omit it out of laziness. Elevations on the Earth are typically measured relative to sea level, but just holding up one end of a tape measure doesn't tell you anything. For example, we've got the 10-foot mark on this tape measure aligned with the top of this dog's head, and this dog is not 10 feet tall. The bottom of the tape measure has to be on the ground if it's going to be something we all understand. Same idea here. We have a multimeter and it's set on volts, and this makes it like a meter stick for electrostatics. It has these two probes, red and black, that have to be connected to something, just like the tape measure has two ends that have to be nailed down. It's not easy to see here, but this says negative 10.5 millivolts. It was jumping around, and the reason is the black lead isn't connected to anything. So this is the same idea as this. Your display, or what the tape measure says here, is garbage. It doesn't mean anything. Now, if I connected that black lead to the battery's other spring terminal, we would have gotten something around 6 volts. We would really be measuring something instead of just this nonsense value. Now, since voltage is potential energy per charge, the units would be joules per coulomb. This is another one of those things that's so common it has its own unit defined. 1 joule per coulomb is a volt. This is also capitalized because, like many of the things this semester, it comes from someone's name. Now, sometimes you'll hear people who don't know any better talk about voltage going through something. This doesn't make any sense. You have to talk about the voltage across things, not through things. So if someone gets electrocuted, you don't say 50,000 volts went through them, any more than if they fell off a cliff, you wouldn't say 200 meters went through them. Now, the connection between the electric field and the electric potential is very important. If we think of the potential as like height, then field is like the slope of the land around the height, at that height. When you were in elementary school, you probably saw contour maps of geologic features like mountains, canyons, things like that. The idea is all the points on the map that have the same height above or below sea level are connected. So we have this made-up example below here. So all these gray lines connect points of equal elevation. Now, we know from Physics 1, if we ignore friction, we should be able to move an object all the way around one particular contour line, I'm using red in this case, at no cost in energy because its gravitational potential energy is not changing at any time. The green contour here, which I'm setting as a lower elevation, if we have to move from the green one to the red one, we will have to do some work. And the energy involved will be mg times the height difference, no matter what path we take, whether we take the very, very short blue path or the long, gentle slope of the purple path. So why would we want to take any path other than this very, very short blue one? Well, in terms of height, this is going to be practically like a cliff face. This is going to be very, very steep. We may want a more gentle climb. Let's say we're towing a wagon or something like that. We may want something, this is kind of a weird drawing, but we may want something where there's a lot more ground that we walk over for the ground we walk up, which means a lower slope. Either way, you're using the same energy, again, if we ignore friction. Now, if we find all the points in space that have the same potential, of course, relative to the same reference point, and join them up to make an equipotential surface, or in the 2D model that we're using here, an equipotential curve, wherever the potential changes by the largest amount over the smallest distance, that's the greatest slope, and that means that's the greatest electric field. So if instead these were lines of constant voltage, here where the blue line is, the electric field would be very large. Out here where the purple line is, it would be small. Same change in voltage, much different electric field. If we keep our two charges in a plane and make the third dimension voltage, again like height, we could also write it like this picture. So we have our height here, this is a higher voltage, this is a lower voltage. Now, I cheated a little bit on these plots, and the reason is, with positive and negative charges, the heights would really go to positive infinity and negative infinity, and that means we couldn't see any detail, so I just artificially capped these values. For the electric field, imagine you shrink down to being very, very tiny, and as you walk around it, every so often you put a ball on the ground and notice both which way, so the direction, and how fast it rolls away. The collection of arrows that you develop would be the electric field. Now, if we required vector calculus for the course, it'd be very simple to write this as E is negative del V. This upside down triangle is called del, and what it means is it's a directional derivative. We treat it like a vector that has components ddx, ddy, and ddz. The idea is it points in the direction of steepest positive change. Now, because we've defined the electric field as a direction of steepest negative change, we have to use this negative sign. I believe the math people do this differently. Now, since we don't expect you to know vector calc, you can forget all this if you want, but you'll see vector calc later if you're in this class in general. You'll have to take it some other time. Without vector calc, we can just write it like this. The E vector is the negative of change in potential with respect to x and y and z. Now, since we're essentially doing things two-dimensionally with a whiteboard or this medium, we can restrict ourselves to one dimension of space and use the y-axis for the electric potential. So in that case, the electric field is negative dV dx. Now, this next question, this has popped up on, I've put this on tests before. Let's say we have two charges that are plus 25 nanocoulombs and minus 10 nanocoulombs, and they're 1 meter apart. If this is a 1D problem, so nothing exists except the line going between these charges out to infinity in each direction, I could say find the point or points where the E field is 0, and then find the point or points where the voltage is 0. Now, we could be very careful with the math and the components, what's positive, what's negative, but to me it's a little bit easier to look at the physics first and then the math to solve these problems. First of all, look at the direction of the electric field caused by each of these charges in all three regions. That's left side, right side, and in the middle. We know the E field always points away from a positive charge, so if we look at the blue arrows here, this is what happens, the E field produced by this positive charge. It's always away, and it's smaller here than here. The red arrows go with the negative charge. It always points towards them. So here these things are pointing in, this is smaller. This will let us figure out this problem much, much more quickly. First, we notice that between the two charges, the E fields are in the same direction. There's no way these can add to give us 0, so I know there's no point in the middle here where E could be 0. I don't have to do any math. Where could it be 0? We can say, well, what about over here? They're in opposite directions. The problem is anywhere here on the left, you'll always be closer to the blue charge, the positive, than the negative, and this is the bigger charge. So if you're always closer to the bigger charge, there's no way the little charge is ever going to be able to cancel it out. The only place we could possibly have E equals 0 is on the right side, where the little charge, we make up for it by being closer to the little charge than the big charge. So the right is our only choice. Now, if we say the point where E equals 0 is x away, on the right of course, from this negative charge, that means it's x plus 1 meter away from the positive charge. So if we set the fields equal, we can ignore the signs on the charges because we've already taken care of all that. And we can say that k times 25 nanocoulombs over x plus 1 squared has to be equal to k times 10 nanocoulombs over x squared. We can get rid of the k's. We can also get rid of nanocoulombs since it's on both sides. And we can write this more simply. We keep simplifying it. Then we expand the denominators and cross multiply. And eventually we end up with this quadratic. Now, we can solve a quadratic equation pretty easily. Quadratic formula gives us two solutions, x equals 1.721 and x equals negative 0.387 meters. Did both of them really work? No, we already have figured out we can't go negative. That puts us between the charges and we know that won't work. So this is a solution that does not make sense for us. The E field will be equal to 0 when we're 1.71 meters away from the negative 10 nanocoulomb charge, and that makes us 2.72 meters from the 25 nanocoulomb charge. Just to be on the safe side, check it. Look at the E field from the 25 nanocoulomb charge and from the 10 nanocoulomb charge. Now, of course, the signs are opposite, right? So we know this would cancel. What about the voltage? If we assume V equals 0 at infinity, and of course the electric field will also be 0 at infinity, but on the test problems I tell you, ignore positive and negative infinity because we know we have zeros there and they're not interesting. So if we assume V equals 0 at infinity, now we don't have to worry about direction. So since V is a scalar. So we could reuse one piece of our reasoning, which is we won't find a point where V equals 0 on the outside of the larger charge, since it would always be nearer. So we can't have V equals 0 out here, since that point will always be closer to the larger charge. So we can look between them and on the right. Now, if we start off and say, all right, let's put our point x to the right of the smaller charge like we just did. Now what we're saying is kq over r, which is voltage, k times the positive charge over x plus 1, plus k times the negative charge over x, that has to equal 0. We do a little cancellation, a little math, we get this, and we can cross multiply to get x equals 0.667 meters. Check the math. If it's 0.667 meters to the negative 10 nanocoulomb charge, it's 1.667 to the 25 nanocoulomb charge. This would be 135 volts. This would be negative 135. We'd get 0. Is there a point in between where V equals 0? Again, we can say it's x away from the smaller charge. This time it would be on the left, of course. This part looks the same, but now the distance to the larger charge must be 1 minus x rather than 1 plus x. Again, this is not very difficult math. We solve it and we get x equals 0.286. So it's 0.286 meters to the left of the negative charge. We check that out. It must be 1 minus 0.286 meters to the right of the positive charge. We get 315 volts in each case. Now, what's the physical interpretation here? Remember that the potential is the potential energy per charge, and the electric field is force per charge. So if we put a charge at a point where E equals 0, that means it will stay there because the force on it will be 0. On the other hand, putting a charge at a point where v equals 0 just means we can move it to that point from infinity for free. And again, gravity is a useful model. We can think of the positive charge like a mountain and the negative charge like a valley. We can find a place between them where the height is 0, which would be sea level, but that doesn't mean we could place a bowling ball there and expect it to sit still. Similarly, if we find a place where the ground is flat so the ball sits still, does not mean we're at sea level. We could redo this example with two charges of the same sign. In this case, we'll get a point where E equals 0 between the charges, but outside that region, their E fields point in the same direction, so they can't cancel each other. We won't get any points where V equals 0, and the reason why, let's go back to the gravitational analogy and think of the potential as like the height of a mountain. We'd have an infinitely high mountain on each charge, and that height would drop off to 0 as we go to infinity, but if both charges are the same sign, there's no place other than positive and negative infinity where the potential would be 0.